this 4 is equal to that equation, right? That's the disk, that's our projection, because it was the widest portion ever encountered. So I'm going to go right here, and this is our projection right here. It's x squared plus y squared less than or equal to 4. Because I set this surface equal to the 4. That would be my disk. What is the radius of that disk? Because I know we're going to want to go polar, aren't we? Put a picture of a disk. There's your disk. But the radius is 2, but we're going to go what? Go polar. You got to love polar, because look. I have this much room to write. I know we can do it. I know we can do it right in here, everyone. There's enough room. I'm going to go polar. So what do you get? Negative. R squared, what's automatic? R. RD, data, there it is. 0 to 2 pi, and the radius, 0 to 2. Does everyone know why I used a radius of 2? I had to think where the surface was equal to 4. Okay. So what is this integral? What's the integral in r cubed? Okay, negative 2 pi, what's the integral in r cubed? R to the 4 over 4 from 0 to 2? What's that final answer? It's negative 2 pi times all that. Oh, I'm getting a negative value. Negative 8 pi. Negative 8 pi. This is the flux across the what? The lateral portion of the parabola. So I'm going to include that here in our notes. Flux across the paraboloid surface. Without the top, right? Is negative 8 pi. And I'll wait till everyone copies this. You'll see where I'm going with the next question. And we're about to wrap it up. The next thing's going to be easier when I'm not going to have to flip this whole board. I think you're going to know logically what to do. So when we found the flux across that top disk that was there originally, true? That was easy. We got the flux across this bottom portion. Then what would be the total flux if I made this a closed surface? So that's part C. Wait, some people are copying. I'm going to wait till you get all this. Flux across the top, this is 48 pi. The flux across that paraboloid, we're getting negative 8 pi, right? Oriented downward. Now, what would be the flux across this included with this? And I say oriented outward. That's my word. Can I erase them? You sure? All right, I'm going to erase. So flux across this surface with a what? Close up this. This is now a closed surface. Aha. And my wording, I say oriented outward. What does outward mean? Well, we know. Just go outward everywhere. Up here, up here, up here. We get it. What would you do with those two numbers over there?
Add them.
Just add them together. That's the idea. So this problem's easy. I don't have to do all that. Oriented outward. It was the what? Plus?
Negative 8.
And what do you get? 45. The reason I did this, that took a little while, didn't it? We only have 2 sections remaining after this. Only 2. One of them is dedicated to closed surfaces because they're kind of a pain. I want to talk about that. Like, you had to do this separately, then you had to do this. What if it had 3 different portions to it? Oh my goodness, Ellen, can you think of a cube? How many sides to a cube? 6 sides. So you're going to get 6 fluxes? Well, yeah, but they all be flat or horizontal. That wouldn't be too bad, right? But still, it's a cool theorem. It's called Gauss's divergence theorem, and it's a one-shot, give me the total flux across, but it only deals with closed surfaces. So when you get to that, we should go back to this problem, and it should take us like 5 seconds to do. Cool? Hey, right before you leave, can you tell me if you got a thing that's on the side like this, how you can get that flux? That'll be the last thing. Like, what if it was like, we did one like this, it was upward, but what if it was like you know, on the x-axis or something. So that's the last one. I'll just compare with you. Let me add something like this. I'll draw it. And when it's over here on the x-axis, and let's just say it's like right here. Do you want to do it at x equal to 3? So there's x equal to 3. I'll get this chunk out of the way. Let's make up a different vector field. How about x? How about 4x, 5y, 6z? That's our vector field. Can you give me the flux across this surface right there? But I'm going to tell you how big that square is, Ellen. That's a square, and it's a 2 by 2 square. So what that would mean, and when you want me to list this out, I'm saying for the y's, I want you to go from -1 to 1 for y, and then for z, go from -1 to 1. That's what I'm saying about that square right there. But the square is, what's its dimensions?
2 by 2.
2 by 2. So maybe in my drawing up here, and with that y-axis, you can go a little bit further. The z-axis goes up, I can go downward, I can extend this. But I'm saying go from -1, z equals 1, z equals -1, and go from -1 to 1 there. But it may look weird because it's over here. But I'll try to make these tick marks a little bit bigger, so you can actually kind of see how it just got. Here's the negative z-axis. Okay. But this is where I got to be very clear about the orientation. So how about oriented in the positive, in the direction of the positive x-axis? Oriented in the direction of the positive x-axis. And when can you find the flux across that s? Which way are they going? So let's put some arrows on here. Oh, they're going this way. Does anybody already know what normal vector we use? It's going to be a unit vector because when that surface is like this, boom, and it's a unit vector that has to go that way. Which is what? He already knows this. So that normal vector is going to be 1, 0, 0. And he hasn't done any of the math. When we parameterize this surface to get to the cross product, he's saying that right there will be 1, 0, 0. Question, what if they said oriented towards the negative x-axis? Then I would have used -1, 0, 0. Does that make sense? But you want to see this coming down? If you're like, I'm not seeing how he knew that. Well, let's play with it. If you parameterize that surface, well, I can't use x and y. What would be a good way to project this? Can you see it? Like, take this and throw it that way. Project it onto what plane? The YZ plane. So guess what I would use? I would use y and z. Does this make sense? I'm parameterizing that surface right there. But it's going to be easy. Y equals y. Z equals z. But what the heck is x? You remember what I told you? This was located where? At 3. It's a constant 3. So what goes here? And that's the parameterization of that surface right there. Yeah, but it's only a square. We'll deal with that in a double integral. So now, check it out. What's ry? 0, 1, 0. What's RZ? 0, 0, and a 1. And what's the cross product? RY cross RZ. And we get 0, 0, 1, we're good. If it's 0, 0, -1, we'll change it over. What do you get? Nope, there's the 1 we thought we'd get. That's a 0, not the 0, right? Should wipe out this here. This times this times this times this. There it is. That's what he knew that from before. So very good. So I'll put that here, and here comes the flux of F across the surface. We call it a surface integral f of r composed of y and z dot ry cross rz dA. So 1, 0, 0, this should go quick. Now I'll just do dy dz, no big deal. Negative 1 to 1, negative 1 to 1. See, that's where I'm going to do my limits of integration. Because they said this, right? So I'm going to build that up right there. What goes here, though? I hope you find this real easy. There's a dot product. Let me go back. Where was that? I made it up. I called it what? 4x, 5y, 6z. So 4x, 5y, 6z. But what has to replace? Because it can only be y's and z's. So what gets substituted at x?
3.
That x gets substituted by that number, or what you saw right there. So that's what I mean, so you know what to substitute there. So what's 4 times 3?
12.
Right again. Negative 1 to 1, negative 1 to 1. So when you're doing fluxes across flat surfaces that are horizontal or vertical, you should notice that the mathematics should come out really, really simple. That's what I want you to discover. What do you get out of this?
12. dA.
Now, has anybody got a fast way to do this integral? So he goes negative 1 to 1, negative 1 to 1, this becomes a 12, dy dz. I can take out the 12 and multiply the area of the what? The square. Well, what's the 2 by 2 square?
4.
12 times 2 by 2. 4 times 12 is?
48.
48. That's the flux across that side. Cool. And again, what if it was oriented the other way towards the negative x-axis? This would have became negative 48 because we would have made this a what? Negative 1. Hey, thanks. I just want to make sure you were comfortable. Like, not everything gets projected onto the xy plane, right? Sometimes you got to project it one way or the other. Super job. Hey, you're going to love that last section. We can do that tomorrow with these normal vectors for the closed surfaces. That's the best part. And then we do Stokes here. It's only 2 sections left. Have a great day. I was going to pass that out.